Mu Sigma Rho, I'd like to welcome you all to this evening's lecture. We're very fortunate in having Professor Box with us this evening. He holds a PhD and DSc degrees in mathematical statistics from London University. He's had extensive industrial research and consulting experience and has held positions at Harvard, Princeton, University of North Carolina, and University of Essex. He's an author or co-author of 6 statistical textbooks, has over 70 published articles. Among the awards that he's received, Benjamin Smith Reynolds Teaching Award for Excellence in Teaching Future Engineers, Guy Medal in Silver from the Royal Statistical Society, the Shewart Medal from the American Society for Quality Control, Wilkes Memorial Medal from the American Statistical Association in the U.S. Army. Last year he was elected a Fellow of the American Academy of Arts and Science. His talk tonight will be on the Los Angeles air pollution study. Dr. Fox.
I'm assuming that you won't mind if this talk isn't very statistical. I'm going to try to talk about some of the statistical aspects of it tomorrow at the seminar. But I want to tell you about a study that we've been engaged in at Wisconsin. Started about 3 years ago, and it's involved myself and Professor Chiao, and also Walt Hamming, who is from the Los Angeles Air Pollution District, and also many graduate students in the department. And what the Los Angeles people asked us to do was to draw any conclusions we could or evaluate some 20 years or nearly 20 years of data, which were hourly measurements of various pollutants at 7 locations in Los Angeles County. And Los Angeles County covers a fairly big area. I'll show you a map in a minute of it. And they have measuring stations in downtown Los Angeles, West Los Angeles, Long Beach, Lenox, Azusa, Pasadena, Burbank. And there's about 20 years of data with about 20 to 30 million numbers. And coming out of that, which are measures of nitric oxide, hydrocarbons, carbon monoxide, sulfur dioxide, particulates, and so on. So there is quite a big problem in getting the data into some form where one can kind of try to appreciate what is happening, so to speak, before one ever gets to the stage of any very fancy statistical techniques. There is just the problem of coping with this large volume of data. Now, if I can show you a map of the area, you can see what's involved. This is about 10 miles, and here's the coastline. Pacific Ocean is down here. And roughly Long Beach, Lenox, and West Los Angeles, downtown Los Angeles, the mountains are up here, and we have Burbank, Pasadena, and Azusa, and the prevailing winds are the way you see them there. So there'll be about 30 miles across this part, and these are where the measuring stations are. Now, what we have been trying to do, and some of this is in a more advanced state than others, we realized that we really weren't qualified to, as statisticians, we weren't qualified to do more than a part of this. And so what we tried to do is to interact with the chemists and meteorologists involved in this, and to, as far as possible, come up with and look into sensible questions in the light of that interaction. And just getting the data out has involved far more of a problem than I realized would be involved. Being able to, if one wants to pick up certain data, wants to look at, say, the amount of ozone which was in, say, Azusa at weekends, say on Saturdays at 12 noon, and having a program which will pick out this information and allow you to get at it is actually quite a difficult problem, one which I can't speak to because I don't know very much about it, but but it is a problem which people have had to tackle. And another device which turns out to be quite important, of course, perhaps in fact the most useful statistical method ever invented was the graph. The likely to be invented, perhaps I should say, was the graph. And so one needs graphical devices to try to understand, provide general appreciation of what's going on. And then when one begins to comprehend what's perhaps going on, one may need new statistical methods to analyse that data in the light of those possibilities. And what I'll be talking about tomorrow, intervention analysis, is really some work which is sparked off by this stage here. And one, of course, would like, as far as possible, to build a model which would describe what is happening in Los Angeles County, and to some extent we made some progress there too. And this is necessarily, of course, an iterative model building process where one is comparing what actually happens with what the model says might happen, and one can't get to that all at once. One has to proceed by easy stages, as it were. So what I'll be talking about tonight is mainly these categories here. I'll be saying something about this tomorrow. I'll be just mentioning one example of that a little later on tonight. And I'll be mainly talking about the analysis of the ozone data, and also some remarks about the carbon monoxide data, which are two of the more important pollutants. Now, let's talk about the ozone problem first. That is regarded, I think, as perhaps one of the most important problems in this air pollution business. The formation of chemical smog, which has made Los Angeles famous, or vice versa, involves a chemical reaction in the air. It isn't just the production of pollutants which causes the smog. It's an actual chemical reaction, as many of you may know. And to get this reaction to go, you have to have the main reactants, which are oxides of nitrogen, which we call NOx, and hydrocarbons. And these come out, mainly they're just coming out of the back end of an automobile. But for these things to react, you have to have these present in fairly high concentrations. And of course that will be favoured if you have a low inversion. In other words, if these chemicals are being held in fairly high concentration because there's an inversion, this will give an opportunity for them to react. And the actual reaction which takes place is a photochemical reaction. And what you get is basically that the oxygen and the oxides of nitrogen and hydrocarbons can react by a complicated mechanism which isn't yet fully understood, but which is photochemical and does require sunlight and produces ozone. Now this was first demonstrated, I think it was Caltech, where it was demonstrated about, I guess, almost 20 years ago now. And somebody backed up an automobile and filled a chamber with hydrocarbons and the stuff that comes out of the exhaust from a car, an automobile, and then they irradiated this was a glass tank, as it were. They irradiated this with artificial sunlight, and they found that what happened was exactly the kind of thing that happens in Los Angeles County. The NO comes down like this, reacting with the hydrocarbons, and forms at first some NO2, and then this eventually, after a complicated series of reactions, starts to form ozone, and so the ozone comes up like this. And you can see that the thing to notice about this is the ozone is formed only, there's a considerable delay. You don't get much ozone until 3 or 4 hours after the initiation of this after the initiation of this. Can anyone hear me doing all that? Perhaps I should. Is it okay? be a bit more cozy here, okay? So this is a typical curve that you get in the lab, and when you start to look at what happens, say in downtown Los Angeles, you see something which certainly doesn't lead one to think that is wrong. You've got to remember that whereas this is a sort of batch reaction, the batch of stuff from the back of the automobile is being exposed to the sunlight, and the whole series of reactions is going on. What you've got to remember is that when you actually get to, say, downtown Los Angeles, that the reactants are continually being pushed into the atmosphere, and of course will vary depending on how many, the input to the system will vary depending on how much of these pollutants are getting into the air at any given time, and of course the traffic density varies during the day. But anyway, this is what the pattern looks like. Hydrocarbons go up something like this, corresponding roughly to when there's a big surge of traffic between about 6 o'clock in the morning and 8 or 9 when people are going to work, and so you get the basic reactants, the hydrocarbons and the NO, and you can see the NO2 being formed a little later, and then the ozone starts to build up, and in downtown Los Angeles it's reached a peak about 1 or 2 o'clock in the afternoon, and it falls off, and the same cycle is repeated again. Now this is that's true of a typical day in the summer. But there is a very strong seasonal behavior here. You have in the summer months this thing goes as I've indicated. You have a strong day and nighttime inversion. In other words, the reactants are held in and allowed to produce reasonably high concentrations. You have weak and stagnant winds, so that in the morning, so that the basic reactants are not blown away. And you have bright sunshine, which helps this reaction to go. In the winter months, the situation is rather different because the inversion usually breaks by noon, and so the reactants are not held in, and the sunlight is much less intense. And you can see that when you look at, if you look at the average ozone levels, you find that in the winter time they're considerably lower than they are in the summertime. Now, if you one way in which you can plot this data, and I believe that I'm not saying that our plots are by any means perfect, but I am sort of putting in a plug for good plots of data, thinking about plotting data in a careful kind of way. This plot, incidentally, is showing the amount of ozone at different times during the day. This is 1, 2, 3, 4, 5, 4 a.m., 5 a.m., 6, 8 a.m., noon, and so on through the day. And this is going through the months, and the colours indicate the 10 through 14 is this colour, 15 through 19 is this colour. I'm saying this colour because I'm actually colourblind, but I have reason to believe that these are different colours. 20 up is this colour, and you can see, I think, that you're getting in 55, you're getting very heavy concentrations in the middle of the day, and that there is a definite seasonal pattern, that you're getting sort of gaps in the winter time here, and things look as though they're getting rather better as things are moving along through the period. So this is, as I say, this doesn't necessarily prove anything, but anyone who ever done any data analysis knows that when you're dealing with, especially when you're dealing with large numbers of values, having good ways to look at data, having good ways to plot data is very important in kind of getting an idea of what is happening, and one can worry about more refined techniques later on. Those people who still believe, as I do, that the greatest statistician that we've seen around or ever likely to see for a very long time, for the far distant future, was R.E. Fisher, will know that in Fisher's book, Statistical Methods of Research Workers, the first chapter is an introductory chapter. The first real chapter in the book, when he gets down to cases, is a chapter on plotting data. And he does, in that chapter, give various ways of plotting data. And it's very important, I think, to see that he was way ahead of his time in this, as with other things, in realizing that that was a very important first step in getting any kind of analysis underway. So in this two-way colour chart you've just seen, you see the sort of daily movement, what's happening during the day. You can see the seasonality pattern, and you can see there's a suggestion anyway of changes in historical trends. The 50s are somewhat better than the 60s, and one has to remember that in 1966 they started to introduce new car engines in Los Angeles with the intention of improving the pollution situation. And there are questions about whether they've succeeded in doing that. Now, remembering that this is a chemical reaction we are seeing, and that there is a rather low velocity but nevertheless persistent wind, what appears to be happening in Los Angeles is that there is this sort of pipeline reaction going on. The reactants are sort of building up in the morning, and then they're being blown across Los Angeles County, and this reaction is taking place as the reactants are going across and reacting with the sunlight. So that if you consider the ozone levels, of course the traffic density is by far the greatest in downtown Los Angeles, but the level of ozone is by no means the greatest there. You notice that over here, level of ozone is 2.4 and 2.2 when you're near the coast, and then 4.0 and 4.5 up here. And up here, where the traffic density is very low, you are finding numbers like 7 and 6.3 and 5, which are very high levels of ozone. So you've got a sort of pipe reactor going, and with the products of the reaction being worst at the far end of the reactor. Those people up in Azusa and Pasadena are in trouble. And you can also see the way in which the NO is being used up. Here you've got 8.5 and 6, 4.5 and 5.5, and up here 2, 3.2 and 6. That's being used up in the reaction. And notice that this isn't correlated very much with the traffic density. 219, 227, 408, 262, 55, 130 and 137. So that's the actual number of density of cars in those different places. And you can see that the ozone level, this is Azusa, that's up there, A to Z USA, that stands for. The citizens of that town decided they would call it A to Z USA, and that's how you got Azusa. And you can see Azusa is suffering from a rather bad dose of ozone. Downtown Los Angeles much less, and Lenox, which is on the coast, much less too. Now, another way of looking at things is from the point of view of frequency diagrams, and this is the frequency of daily maximum hourly readings in various ranges, and this one here is 50 and up, this is 20 to 49, 9 to 19 and 8 and below. So you can see that there's some suggestion that the situation is in fact improving, because the frequency of, say, 8 and below is increasing. That's to say, the frequency of an acceptable standard. That's the one of the standards. The standards vary. This is the federal standard, 8 and below, and you can see that that's the proportion of times the standard's met is certainly apparently increasing over that period. However, that's in downtown Los Angeles, and the situation is less good in Azusa, which is up there by the mountains. In fact, you can look at a whole set of these diagrams for the these are more or less in geographical position as to see what's happening, and nothing much is happening apparently at Pasadena and Azusa. Those don't seem to improve very much. So a preliminary analysis of the data suggests that in downtown Los Angeles, the level of ozone is lower in the 60s compared with the 50s. There have been progressive improvements since 1966 perhaps, and appreciable differences exist between locations. Now we can be more specific about that as we go on. So that's what I want to say about, for the moment, about ozone. Now, one of the reasons for carbon monoxide is something that gets people all head up, because they know that people sometimes kill themselves by breathing too much carbon monoxide, sometimes deliberately, from the exhaust from from automobiles. And I personally don't think that carbon monoxide is a really big hazard, but nevertheless there are people who do. One of the reasons I don't think it's a very big hazard is that, for example, people who smoke cigarettes are inhaling about 120 times the amount of carbon monoxide they'd ever get from the worst situation they'd ever be from car exhaust. But still, whatever you think about it, carbon monoxide is regarded as an important variable, and it is an interesting variable, because it ought to tell us something, if nothing else, about the number of automobiles that are actually around, because carbon monoxide is more or less inert as far as it isn't like the oxides of nitrogen and the hydrocarbons. It doesn't enter into a chemical reaction, it just hangs around. And if you look, for example, at downtown Los Angeles, and you say Saturday, Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, you find there is a Saturday and Sunday you have a different pattern, but at Mondays, Tuesdays, Wednesdays, Thursdays and Fridays you have this pattern. You notice this big pattern here corresponding to the rush hour in the mornings. And one thing you notice is, one thing you wonder about is what happens in the afternoon. I mean, these people go to work, but when do they ever come back? And you can see the same kind of thing for the other locations. Well, let's take a look at that a little more closely. Here's a picture showing that the average of all Mondays through Thursdays, this is parts per million of carbon monoxide at different times in the day, and you can see the morning rush hour, and you can see something happening in the evening when they come home, but it's a much lower level. Now, they really do come home, because if you look at the traffic volume, here's a picture showing the traffic volume, and here's a bump here in the mornings and another bump here in the evenings. And I guess they take a little wider bump there, and so it may be a little higher here. Wider spread perhaps here than it is there. But anyway, you've got a couple of bumps which seem fairly respectable, but you don't see those bumps reflected in the carbon monoxide, and one wonders why that is. When you talk to the meteorologists, of course, they immediately say, well, a factor there is wind speed. That would be probably the most important factor. And this is the way that the average wind speed changes during the day. And you can see that what is happening is that in the afternoon, typically you'll get stronger winds. The winds there are never very strong, but they are, an average, say, of 5 miles an hour in the middle of the afternoon, whereas down here they're perhaps 1.5 miles an hour. And so one might think in terms of modelling this in a very elementary way, and what one should do, I think, with modelling very often is to start off with a simple-minded idea, and then develop this as it seems one is forced along the path of learning, so to speak. Well, naively, if you really didn't think too much about it, you might say that the carbon monoxide might be equal to some constant plus a constant times the amount of traffic. Now that would, if we forgot all about wind speed and so on, this would simply be saying that there's probably some carbon monoxide which is hanging around anyway. There's a background level, say beta 0, and then there's the actual traffic produces at a given hour produces more carbon monoxide. But there's two things that are obviously wrong about that. One is that they don't allow for the wind speed, and the other is they don't allow for the cumulative build-up of carbon monoxide. Now what I mean by that is that one would not expect that the amount of carbon monoxide which is, say, present at, say, 3 o'clock in the afternoon is a function simply of the amount that's been put out at 3 o'clock in the afternoon. You'd think that it would be a function of the amount put out at 3 plus some residual amount that was put out at 2 plus something depending on the amount that was put out at 1 o'clock and so on. In other words, if a tremendous amount of carbon monoxide was suddenly put out at, say, 1 o'clock, that some of that material would still be around at 3 o'clock. And so one has to have a model which would allow for this kind of thing. And a simple model that one might try anyway would be to say, well, let's try to get the wind speed in by saying, well, we would think that the more the wind blows, the more it dilutes this, and discussing this with our colleagues in the meteorologists, they suggested the wind should be to some power there as an approximation of the effective wind speed, and that also the question of the traffic density, I've put T twiddle sub T, and T twiddle sub T is some kind of weighted average, which is a reasonable kind of model would be to say it's the amount which is being put out by the traffic now plus delta, say, times the amount put out at T minus 1 plus delta squared times the amount at T minus 2 and so on. It's very easy to come up with mixing models which would describe that kind of behavior. And so what one might do is to see whether a model of this kind with suitable values of beta 0, beta 1, alpha and delta, which would be the discount factor in this model, would fit the data or not. And these are some results which we got. This is estimates of maximum likelihood estimates of beta 0, beta 1, delta and alpha with approximate standard errors, and you can see that they look as though they're reasonably well estimated, and in fact a model of that kind, although it's very simple, does account for a tremendous amount of the variation. You can see what's happening here with the actual, with the dots, the line which joins them, and the predicted, which is the circle. So with one can, in fact, it does seem that that will work, and it also works for different locations, and we have 7 different locations, and we find that models of that kind work for the different locations. Now, one way of one question which we found intriguing was this: that we had, it turned out that in Los Angeles, the traffic data we had was gotten in the following way: that there's a certain day, it's the second, I think it's the second week in May, and it's always a Wednesday, and what they do is they put these little strips across the road, and they count every vehicle that comes in to the city and every vehicle that goes out, and they actually determine that's the way they determine the vehicle density throughout the day in downtown Los Angeles, which is the data that you saw on the traffic. And trouble with that is they do that every year, so that there's no way of knowing what the traffic's like at weekends. So one of the things we did just for fun was to say, well, we would like to know what this would forecast. Obviously the traffic would be different on Saturdays and Sundays, so we can take our formula, our simple-minded formula here, and work it backwards and say, since we know what the CO is, let's see what this says the traffic density would look like on Saturdays and Sundays when we don't have any data or we didn't have any data for Saturdays and Sundays. And So looking back on that, and this is what we knew, this is the traffic pattern for the weekdays, and this is what the traffic pattern is estimated to be. We estimate it to be for Sunday and for Saturday. And we did eventually manage to get some other data on that. This isn't actually for Los Angeles, this is from, I think it's Pasadena, but there was a location where they did get some traffic density values, and we think our picture of what the traffic pattern is and the actual traffic pattern in that place are rather close. So this is kind of a rather an elementary exercise, and we're doing a little better than this now, but this is rather an elementary exercise in model building, just a sort of initial start off. Now one has to be very careful about data that you're presented with. In fact, not only should you say, in my opinion, not only should you say that all models are wrong. In other words, the way to start a statistics course is to say to the students, you know, all models are wrong. There never was a straight line, there never was a normal distribution, there never was an exponential curve, there never, and so on. You know, models are sometimes useful, but they're always wrong. Because if you're not very careful, people get hypnotized into believing their model, and you know what happened to Pygmalion, you know. Not only are all models wrong, but all data are wrong. If you collect together more than, well, that's any number of observations, but certainly if you collected more than 20 observations, the probability that one of the observations, at least one, would be just wrong becomes very large indeed. And of course, many of our statistical techniques are saying the following model is true for u equals 1 through n. And that is a statement which you know to be untrue, or at least with a very high probability you know to be untrue to begin with. And so one is, of course, always on the alert to, in any sort of real data, to expect the data might be wrong. Well, here's an example of that. In 1966, the new cars were introduced, and these are the carbon monoxide levels in Burbank, Pasadena, Azusa, and so forth. And the thing you notice is that, and the thing that was claimed was that there was a very big drop in the carbon monoxide levels. We had Walt Hamming, who was working on this project with us, is a physical chemist. He's also a very obnoxious kind of character. I love obnoxious characters. I mean, he won't let you get away with anything. He argues with you. He's like Kempe, who's a great help to us all because he won't let us get away with anything. He tells us when we're wrong and sometimes when we're right. And those people are extremely valuable because they just say we don't believe it. And I guess we might have let this thing go, but what Hamming said to us was, I just don't believe that. And he said, I think what happened was that they must have changed the method of determining carbon monoxide sometime in there. And in fact, we found out on making inquiries that the method of determining carbon monoxide had been changed in April 1968. And I'll talk about that a little bit more tomorrow because we can estimate this a good deal more precisely if we use more precise statistical methods. But it does turn out, as you might guess from looking at this data, that what has really happened is that there has been a calibration change which has occurred here in '68. Actually, the measurements, it's possible to show that the measurements made here were about 5 units lower than the measurements made there, simply because they changed the method of measurement, and that the apparent improvement is only moderately, a very small amount of it is due to the automobile exhaust control. And everyone knows that if you want to improve data, the best way is to change the measurement. It's much simpler than, in fact, these are estimates, which I'll show you again tomorrow, of what that adjustment amounted to, and that is quite a substantial amount. These are estimates of what the yearly trend since the introducing the new car engines was, which are quite small numbers, and actually most of them are either not significant or barely so. Well, I'd like to show you a piece of sort of detective work that was done on this. The question is, why this discrepancy? And one of the clues was that at the time that the calibration change was made, a device was installed to dry the air sample. So the discrepancy could be associated with humidity, and so one thing we did, and we're getting involved in arguments in these people, they said that what we'd done had made no difference. What they'd done had made no difference, and what we showed them eventually and persuaded them was, one of the things that persuaded them was we plotted the differences before and after in the same month. We said, okay, let's take some Januaries before you made the adjustments and Januaries after you made the adjustment, some Februaries before and after, and so on. And then we can get an actual measure of what the humidity was in January, February, March, April, and so on. And we can adjust that to get a measure of absolute humidity. If we plot the absolute humidity against the difference, you can see that you get something which looks like a relationship there. And this is one of the things which eventually persuaded them to check the method, and they did eventually show that their old and new methods did differ by about 5%, and since the amount you're determining, about 5 units, and since the amount you're determining is about 10 units, that corresponds to about half the number. Well, I guess I should end up on some kind of, I've told you something about the air pollution data. I might say that I think that everyone's enjoyed this study. I'll tell you some more tomorrow if you come to the statistics department seminar about some of the statistical methods that have come out of this, which involve analysing this kind of data. You know, what are some of the spin-offs out of this? Well, I think that one of the things that's been very good is that the graduate students, there's been about 6 to 8 graduate students involved in this study, and they've all worked very hard and they've all been very enthusiastic, and we've had a lot of sessions on trying to figure out what was going on with the data, and they've done a lot of hard work with the computer. It's terribly difficult to cope with just these large numbers of data and getting the stuff out of the computer and things like that. It's easy to dismiss it, but it is in fact a very big problem, and they've coped with that. And I think that they've learned something about how you actually do analyse data. And perhaps I could end up by saying something about my philosophy about, or I don't know if it's mine, it's not mine, I guess it goes back to Aristotle, but anyway, what a philosophy would be about the way in which an investigation goes. There used to be a discussion among the ancients about whether everything should be, as it were, deduced from some theoretical principle, or whether you should only be concerned with data or practical things. But of course, for a very long time it's implied by what Aristotle says, and certainly in writings of Grosseteste and Bacon, it's clear that that it's understood by them that what you have in fact is an interaction or an iteration going on between practice and theory, and that it isn't that this is right or this is right. It's that what you have to have is the data suggesting a theory, and the theory suggesting the way in which you should get more data, and so forth. It's rather like an interaction I sometimes like to think of this. I said in somewhere that the theory and practice like man and wife in a happy marriage, that one complements the other, and without interaction between them there can be no new life. And that is, I believe that to be true. The idea, for example, I've heard it said among statistics departments. Somebody called me up at Wisconsin and said, "Are you a department of mathematical statistics?" It was some government agency, and I said, "No." And he said, "Are you a department of applied statistics?" I said, "No." He said, "Well, what are you?" I said, "We're Department of Statistics. We're not half a department, we're hopefully all of a department." I feel very strongly that the separation of these two things is very bad. And now what happens when these things interact? You get some sort of hypothesis or model or conjecture. You make a deduction from that, you consider consequences, you compare them with the facts, and by a process of induction you perhaps arrive at some, well, you perhaps confirm the hypothesis, but more often you arrive at some modified hypothesis which replaces this. And what sometimes then happens is that you have to get involved in a different loop. This is a kind of iterative thing around here. But at some point you may find that you just don't have the appropriate data in which you can carry this process any further. So then you have to go up through this loop, and you sort of hold a window up to the true state of nature, and you have the option of designing the experiment, of putting this window and deciding which part of this you'll try to illuminate. But you only see through a glass darkly. You only get your results subject to error. These results are exact, but they're subject to error. And of course the hypothesis which you're comparing it with may be wrong. So that you're comparing data which is basically has the disadvantage, but while it's exactly produced by the true model, as it were, because it's produced by nature. It's subject to error. And you're having to compare that with your present concept of what the model might be, or what the... So this basically is an iterative process, and it does involve, one has to remember that it does involve this kind of thing, and that a great deal of judgment goes into this. It's no use talking as if, you know, when people worry about whether it should be the 5% point or the 6% point, but very much more important than all this is that somebody is having enough sense to consider these variables, or to get this particular set of data, or to look at that particular aspect of the thing, and so on. And the design of an experiment can determine whether variables are ever looked at, or whether they're ever looked at over the right ranges, and so on. So they're very much more important than those other considerations. The other considerations get a lot of publicity because they're easy to formulate mathematically, whereas this isn't. But the question of how easy a thing is to formulate mathematically shouldn't be the criterion on which it's whether it's to be considered or not. Well, one could go on talking about this kind of thing. I guess that that this is a major iteration, as it were, that goes on, and it goes through different stages. You just saw some of the stages, very elementary and early stages, in this look we had at some of the Los Angeles data. We hadn't gone very far down the road, but we had made a start anyway. And I'd like to just end by pointing out to another iteration which goes on, which is also occurring in this process, which is this business of inference, and what I call criticism. It's a word due to Cuthbert Daniel. It seems to me that this one gets a lot of publicity. If we have a tentative model, we want to see what that model means. We are very prepared as statisticians to act as a sponsor for the model, to work out what would be the most precise method of estimating its constants, for example, or its parameters, given that that model, and this is a conditional statement, given that that model is appropriate. So, and this is called the process of inference. Now, in recent years, Tukey and Anscombe and Daniel and people like that have emphasized the importance of this other process, which is having made, as it were, a tentative analysis which is based on this inference, one changes one's role from being a sponsor to being a critic. In other words, to be a good statistician, everyone has to be schizophrenic, which accounts for how peculiar we all are, the good ones of us, that is. Not too many of us. You having sort of accompanied the model this far, and you have not to fall in love with it. You have to suddenly rat on the model and say, okay, now I'm going to be a critic. I'm going to look at residuals. I'm going to become very picky, and this is this criticism part, which leads possibly to either to your acceptance of the model, or as a tentative description of what is going on, no more, or possibly to its modification. So, in case there are some people here who, perhaps some students, who might listen to this kind of plea, I want to tell you that I believe that whatever may be the future in pure mathematics or whatever for those people, I believe there's going to be a tremendous demand for good statisticians, like the statisticians that have turned out from this university. And the reason is because people are realizing now that the world faces very serious problems of population, problems of pollution, problems of energy and so forth. And no matter where you look, you'll find that the thing that's missing is the basic data on which to go on. A lot of people want to do things, politicians sort of run around in all directions and do things, but sooner or later they're going to realize that just doing things isn't enough, that they have to do sensible things. And to do sensible things, they're going to have to find out what is happening. And sometimes what is happening is rather complicated. And the only way you can find out is to try to get data, try to do reasonable analyses, and try to understand what is happening. The Environmental Protection Agency now, I think, is a very weak agency, and what it's going to have to learn if it's going to be effective is that it has to get good data, and it has to get people in there who know something about dealing with data. But I'm certain that the demand for good statisticians in solving the world's problems is going to become greater and greater. And that whatever the unemployment problem is going to be in other areas, it certainly won't be an unemployment problem for good statisticians. And I say statisticians, I don't say applied statisticians, I don't say theoretical statisticians, I say statisticians, because statisticians are people who know the theory and can apply it. Thank you.
Some minimum where below that or up to that it really isn't much effect, but beyond it really is affecting the respiratory system, etc., or had the study gotten into anything of that sort.
Thank you. There was a conference which was held last year in the Washington Academy of Sciences, in which many medical people were there, and I gather that the basis on which these levels are set varies very considerably. The validity of the basis varies very considerably. I think in some instances it's much better based than others, but in some instances it is known. Well, for example, in the Los Angeles study, one of the things they did was to get people to put their head in the chamber, and they measured levels at which people would start to produce tears and levels at which they would start to complain of chest conditions. And they also know something about the increase in mortality with people with lung difficulties in times of bad pollution. Now, sometimes the conclusions drawn from that are very weak. Like I've seen it argued that carbon monoxide is very bad because on days when carbon monoxide is very high, there are a number of extra deaths in this area, and you can show that's true. But of course, it's very likely there's not the carbon monoxide that's doing it. It's very likely that it's one of these pollutants like the ozone things. It's not ozone itself, but the complexes that ozone forms, which is actually doing that. So I believe that the basis on which those levels are set, in some instances, are probably realistic. In others, they wouldn't bear really examining very closely. But I really think that I think they're probably right in setting some levels, just on the basis that, I mean, we all of us do this. I know sometimes, you know, like in a faculty meeting, and people can go on arguing forever. So a very good project is to simply say, for someone to say something, you know. I suggest we do something. Now, it's very often a good idea to say this, even though you don't really believe it, just because if you say this, it will crystallize the argument, so to speak. And if you set the standard and say, well, the standard is 8, well, you know, this gives an opportunity for some people to come along and say it should be less than 8, and some people to come along and say it should be more than 8, and at least you've got something to argue about. So I think they do provide good arguing points, but I think that there ought to be more interaction between these levels and the scientists involved in these studies. And
May I
yeah.
follow that up
Yeah.
another question? And that is, you mentioned these different levels at these different locations.
yes.
Now, I wonder if there might be some, or maybe there has been, attempt to do some epidemiological studies. Now, I do know that people who live in one area, this is very mobile citizenry in this area. But maybe the people who stay at home most of the time, the women, maybe the children, not the women, the children, as contrasted with people who are subjected to this. I was thinking of an epidemiological study following this up, or maybe there has been already.
No, I don't think there has been. Of course, you know, there have been in things like steel plants and things like that, and there are some of those excellent ones. But so far as I know, not in this area.
Another general question. This picture that you gave about the processes of statistics, the processes of knowledge, is one with which I suppose people in the statistics business will accept rather definitely. They may alter the configuration somewhat. Those are matters of detail. I'm just wondering, it seems to me, and I surmise that you agree strongly, that this isn't just the picture with technology or applied research. This is the picture of the whole knowledge mix. Now, my question is this: do you find any awareness of this sort of picture amongst philosophers of science or logicians or what you will, who are supposed to write, people outside statistics who write on the scientific method? Do you come across any of these people who have this sort of picture?
I've come across some people who haven't. Popper and people like that.
No, Popper, because Popper has one point that the falsification is a sort of a criticism angle.
Yeah. Well, no, I don't think that this is sufficiently. I think there are some people who do. I should try to remember. There's. I saw an article in Science once, which is an editorial written by a British scientist, which was saying something rather like this about the way in which science actually occurred. He wasn't a statistician.
There's a short book by Peter Medawar
That's the guy,
who published Philadelphia, which gives this sort of picture.
That's right. Peter Medawar. Well, yeah. And I think he probably understands it, but I don't think it's what I understood it should be. I believe it's important to say. I mean, I think we agree on this, that it's important to have some kind of pixelated sequence, because otherwise it isn't clear what we're trying to do. Yes.
George, did you do anything explicit about the temperature reversions? Is there any pattern to those?
Well, yes.
You didn't have them explicitly in your mind.
No. Well, we did have. That's a very good point. We believed that there should be In the model that I showed, it was just wind speed and that was it. We did originally have a term in there for temperature for the inversion level. We don't have very good information about the inversion level during the whole day. We only have the inversion levels taken at, I think it's 8 o'clock in the morning. And those, we had established some correlations with those, but not in that particular model to see those. And actually, we couldn't, in that particular model, we didn't establish any relationship.
Yeah, for the ozone, where you've got chemical reaction labs.
Yes, in that case, we can.
But so far you haven't.
Well, yes, we do have a model which involves temperature at inversion level for ozone, but I haven't, that involves it. What we're trying to do now is to get something which is a sort of, see, the problem we're in is that if you try, and it's the usual sort of universal problem in modeling, if you try to model everything, you're in trouble because you've got a lot of different variables.
Got a lot of data.
Yeah, you've got a lot of data, because if you try to model everything, it's still not enough, or even that. But if you try, so we have to have something which is sufficiently simple to predict, and yet doesn't, which is ridiculous in the sense that it does represent something different. And what we seem to be getting to now is when we had a model which began with kind of a box, in which the either box was inversion level, and you imagine this reaction is going on. And then the question is how many terms you take in there. I mean, the kinetic model which chemists come up with is horrendous, so you've got to describe that somewhat more simply. And we have a guy working with us called Pat, who is a engineer, and we seem to be working towards a model there which will take into account, as far as those are concerned, will take into account inversion levels and also the different, bar inversion levels, atomized concentrations of initial reactions will more or less account the ozone.
I have in mind, as I remember, having seen some of this story, you've got the mountains behind, you've got the wind pushing it in, and inversion, you've got a sort of tank.
Yeah.
See, an equivalent volume of tank might be a good.
Yeah, well, that is basically this thing that's
Sure.
up to the top one.
And you have the mountains inland, and of course,
That will work fairly well for us. Once it, and Azusa is a different problem. I'm not quite sure why that is.
is there a sort of escape?
Well, there's some serious theories about wind and a lot of heavens, but that may not. I guess we've got to truth is the other model which counts as some of it is not always.
Well, it's clear from what you've said, this is very much an interdisciplinary study, but I was wondering, you're getting at it towards the end, to what extent, in fact, you involve other people, to what extent you consult them in this kind of study?
No, I think that's wrong. You mean,
What sort of people? You mentioned meteorologists.
well, our main source is mechanical, with some meteorologists, with our main sort of immediate source of mechanical, sort of meteorologists who work in this area for about 20 years in Los Angeles. He's actually rather of the Hammock, which the American analysis analyst, really not neat guy. He starts off by saying, oh, this is all nice, so he's to tell you, and then you have to question, you have to talk to him, because otherwise interact. But a lot of, we've got a lot of good, he's retired from Los Angeles now, but he's still working on this project. Spends quite a bit of time. I don't think we would get very far. I mean, well, the main thing is we wouldn't get very far on our own because we don't know enough about meteorology and pollution and physical chemistry and so on. But we can do quite well when we're interacting with them, and then it tells us if it's something.
American Society of Mechanical Engineers as to how to appropriately sample some of the things that people are looking at. Now, you chose only to speak of ozone and carbon monoxide, but if you take the particulate matter that was one of your primary pollutants that you listed earlier, you find that there are still controversial techniques in making those measurements. So one does have to look at the data that one has with a very skeptical view. And I appreciate your comments on encouraging the students about the field of statistics. Speaking for the engineering community, I realize I'm sticking my neck out in doing that, but I think I can do it fairly. We have a great need for statisticians now. It's just beginning to be appreciated. We're just scratching the surface in learning how to design experiments effectively, asking the question, how much data does one need to take in an experiment? And I think it's going to be you people that are going to help provide those answers.
Thank you. I think, one of the things I'd like to see done, I mean, very, very simple kind of thing, that I'm going to try and get, I don't know whether I can persuade anyone in the Environmental Protection Agency, perhaps the people who cooperate with won't have the authority to do this, but what I'd really like to see done would be cooperative studies. Now, whenever cooperative studies have been done, and we used to do them, when I worked for ICI, we used to do cooperative studies quite regularly, and the Bureau of Standards, ASTM, people like that do these. And they're always, whenever I've seen them, very informative and very useful in the sense of, which we're talking about just now, about just throwing something into the arena and getting a big fuss made and then getting people to settle down and figure out what's going on. Now, what these studies are, of course, for people who don't know, is that you essentially you try to arrange that several sets of people analyse the same sample. And you try to arrange to send these samples around, or if necessary, bring the analyst to the same place and get them to analyse the samples. And to avoid embarrassment, you can sometimes arrange that results are published so that lab A you identify which is lab A, which is one colour, which is lab B, C, D, E, F, G. And that's sometimes necessary because typically the way these, anybody who's ever worked in these cooperative studies knows that what happens is that lab A produces results like that, and lab B produces results like this. These are the same samples. And lab C produces results like this, and lab D produces results like that. And when you show these results to the different labs, they are incredulous. They say, how can it be? This is nonsense. Lab A says that was 5.5, and we can reproduce those results to within 0.05. And here are these people saying it's 4.6. It's rubbish. They don't know how to do the analysis. Now this